everybody. Uh, Nobody showed up to this one, so I've opened up, well, I've turned on the projector anyway, just in case someone walks in while I'm in the middle of this and wants to hop in, but right now I look like a crazy person because I'm sitting up front with this weird little headphone thing on, and I'm going to talk to an empty classroom, but let's be honest, that's not much different than most afternoons here, so I'm down with that. So as a result, I'm probably, unless somebody comes in, I'm just going to quickly go through this PowerPoint, seeing as you can rewind and pause the video if you want to. So I'm not going to wait for people to jot stuff down, and this may end up being a little bit shorter. A few details about the test. Just like test one, it consists of 90 minutes, so you'll have the full lab block to do it. A lot of times I don't expect it to take the full lab block. It very well may, and probably for some students in each class period it will. But for others of you, you may finish up a little bit early. And if that's the case, be sure you bring something else to work on or something else to do to keep yourself entertained, because you're going to have to hang out in this general vicinity for the full 90 minutes. Just like last time, the test will consist of 15 multiple choice questions. Those are 2 points each. One lab-based question, and this is essentially, here's some data that JRandom has collected. What results should he find with that? A lot of times with these lab questions, you honestly could answer it if you just understood the concept behind it, even if you don't necessarily remember exactly what you did in lab, so that's a good thing. And then 5 free response questions, each of those worth 10 points. Keep in mind, I do give a whole lot of partial credit, but only if work is shown. If all you're doing is jotting a couple of numbers down and then an answer, there's not a whole lot I can do for you. Honestly, the numerical answer is really only worth like 1 point out of 10. I'm more looking for the process, so the more you can show me, the better. The worst thing you can do is to write nothing, so be sure that no matter what, you just give me something to work with. Show me that if I ask for a velocity of something in orbit, show me that you at least know what velocity is. Put down the correct units in the little answer box. Just show me that you understand something, because if you hand back something and a problem is totally blank, there's not really much I can do with that. That's 10 points off. That's a whole letter grade to begin with. So just something to think about. Bring 1 sheet of paper, front and back. This is an 8.5 by 11 standard notebook or computer size piece of paper. And make sure you bring a calculator that is not your phone, because you can use your phone for other things beyond calculations. So I need you to have a non-internet connected device to use as a calculator. So let me know ahead of time if you need to borrow one. That way I'll know there's enough for everybody. I'll have it set aside with a little sticky note with your name on it, and we'll be good to go. The first thing that you're going to need to know on this test is Newton's first law. This one's often known as the law of inertia. We have somebody. I did not expect that. Yeah, so we just got started. So yeah, Newton's first law is often known as the law of inertia. Inertia is just an object's tendency to keep doing whatever it's doing. So if it's not moving, that means it will continue to not move. If it is moving, it means it'll continue to move in the same direction with the same speed, unless acted on by an outside force. So if I slide this little piece of this paper towel roll across the desk, it slows down and stops, but it only does that because of friction. If this were a 100% frictionless surface, then it would have continued to slide in that direction for forever, if there had been no friction and no air resistance. So that's important to know. The second law, honestly, comes from exactly the same idea. If you move in the same direction with the same velocity, that means you have no acceleration. Or if you stay completely still, that means you have no acceleration. And Newton's first law is saying that if there's no outside force, there's no acceleration. The second law is basically the other side of that coin. If there is a force, there is an acceleration. One important thing to note about this, an object can have a bunch of forces acting on it at once, but it's the overall total net force that will equal the object's mass times acceleration. And by the way, this will work in different dimensions as well. If you're only looking in the x direction, I could say the sum of all the forces acting in the x direction, or the sum of all the forces that have components in the x direction, the sum of those components, will equal mass times acceleration in the x direction. Same deal in the y direction. If I know all the forces acting in the y direction, then I can say it equals mass times acceleration in the y direction. Or if I know the grand total force overall, it'll equal mass times the acceleration overall. So for example, if you've got a sprinter who's about to, I just hit my elbow. Ugh. That's okay. I'll be all right. I'll weep about it later by myself. If I got a sprinter right here, who's accelerating to the right, then I can still use the y equation, because the sum of all the forces in the y direction, even though he's accelerating to the right, is going to come to 0, because there will be no y acceleration. So I can use that to figure out this guy's normal force. Because the normal force minus the gravitational force will equal mass times acceleration in the y direction, and even though there's an acceleration to the right, there's no acceleration in the y direction. That'll tell me the normal force is the same as the force of gravity. So I got a little bit rambly there and a little bit more in depth than I meant to. But it's kind of a closer look at what this means. This overall equation, I found some students were forgetting when I asked, you have the total force, what is the acceleration? Never forget if F equals ma. This is the holy grail equation of physics. This is absolutely beautiful. This is wonderful. F equals ma. It's a lot of boxes, and it deserves a million more boxes. All right. And then we've got good old Newton's third law. The third law says that for every action, there's an equal and opposite reaction. If I've got two objects, A and B, then the force on object A exerted by B is the same as the force on object B exerted by A every time. So if I pick up this pen and slap it back down to the table, the pen has slapped me back with the exact same force. The pen accelerates a lot more because under the same force, since it has a smaller mass, it has a bigger acceleration. And acceleration, a lot of times people confuse with force. So that's an important thing to keep in mind. A lot of times you don't necessarily see that when you draw a free body diagram. A lot of times I'll see forces that don't necessarily balance each other out. So why is that? Why don't I always draw a down and to the left arrow if there's an up and to the right arrow on an object? If you want to. Yeah. All right. So the reason is when you're drawing a free body diagram, you're only looking at the force on one object at a time. Newton's third law basically says if this runs into another object, then this will experience a force one way, this will experience a force the other way, and those two will be equal. But for most of the free body diagrams we do in class, we only look at one object at a time. So that would look something like this. So Newton's third law doesn't often show up in free body diagrams if you're only looking at one object, but it is an important one to know. Speaking of free body diagrams, you need to know how to draw them. I'm not picky about how you draw a lot of your pictures, but free body diagrams are very specific in how they're drawn and keep showing up in a bunch of different types of disciplines. So a few things that you need to know about it. One, all the forces on an object are going to originate from the center. Specifically, it'll be the center of mass, at least for now. We're going to get to a point soon, toward the end of the semester, where you're going to have to pay attention to the forces where they're actually physically acting on the object, because that'll make a difference. But for now, just treat it as if they originate from the center, all the forces. They also point in the direction they're acting on the object, not the direction an object is acting on something else. So if this thing's resting on the ground, wow, that's a weird ground here. There we go. It has a gravitational force, and that's pulling down on the box. Now, like I told you about universal gravitation, every object with mass is attracted toward every other object with mass. So the box is actually exerting an upward force on the Earth, but I'm not including that because I don't care about what the box exerts on the Earth, only what the box feels. Forces acting on the box. Now, that said, the Earth is pushing up on the box from the ground. That's a normal force. So that vector also originates from this little center dot, and it points in the direction that the box feels a force as a result. If I show up, and here's my, let me do a quick little Martin sketch. There we go, looking pretty good. Yeah, and then I push this box. There will be a force of my push, and that'll originate from the center of the box and point in the direction I'm pushing it, and friction will push back against me. So that'll be to the left in this case. One other point about free body diagrams is that I only want to include forces acting at the moment. I do not want past forces. So if I let go, the moment my hand loses contact, this push force is gone and should not be included in a free body diagram. Even if the box is still moving to the right because I had pushed it in the past, it should no longer be a part of the diagram because there's no longer a force to the right. In fact, it'll probably slow down as a result of this friction, pointing in the opposite direction of motion. So that's the other thing about free body diagrams. There does not have to be a force in the direction that it's moving. That having been said, there could be. There does not have to be a force in the direction of motion, of motion. But there can be. That trips people up a lot, a whole lot. So be careful about that. Wow, that was not neat writing. All right, I got a few more tips for you about free body diagrams. First and foremost, you want to use simple drawings. If you make it a little bit too complex, your vectors can get lost in the various lines of your drawings. So I'm never going to take off points if you just use a dot or a box to represent any sort of object. That's totally fine. You do want to take every force into consideration, and I'll go through the most common forces you're going to face in just a second here. But take the time to actually sit back and think about what you're doing and what's happening. If an object is not moving or it's moving at a constant speed, and you have a rightward force but no component of any force pointing to the left, that's probably a problem. You might have left something out. Vice versa, if something is accelerating in a certain direction and there's no component pointing in that direction, that's probably a problem as well. Typically, when you're drawing your force vectors, if you know that one force is bigger than another, you're going to want to draw that with bigger arrows, and the smaller forces get smaller arrows. I'm not going to go crazy and take off points. If you want to get really, really technical about it, a force that is twice as strong should have twice as big an arrow. But I am not about to sit down with 90 some of your tests, take out a ruler, and make sure that every force is proportional to its magnitude, because that would just be insane. But that's just a general a rule that you could follow. And I already mentioned this, but do not exert any or include any forces the object is exerting against something else. Physics is a very cruel, cold subject, and if I ask you about a certain object, that's the only object I care about. And I don't care about how it's making anything else feel in the universe. I only care about that one. So physics only cares about itself, not anything else. It's very, very, very selfish. The most typical forces that you're going to come across are the following. You've got gravity. Now, weight, a lot of people confuse with mass. Your weight is not equal to your mass. Your weight is a force, and it happens to be the force of gravity acting on you. This can always be calculated as mass times 9.81. A common mistake I've been seeing this year is people just putting 9.81 as the force of gravity, and that's not necessarily true. Oh, by the way, that's only on Earth. I should probably put a little asterisk here and say on Earth. If you are somewhere out in space or on another planet, you're going to have to go the long way to find the force of gravity, and that's capital G times the mass of the planet or object. Mass of object 1, I'll just say, times the mass of object 2 all over r squared, the distance between them. This, honestly, your little mg, that's the Earth equation, is really just a shortcut. Lil g happens to equal big G times the mass of Earth over the radius of Earth squared. In previous problems that we've worked, I've given you the mass of Earth and the radius of Earth, so you can test this out on for yourself. But if you just take this, which comes to 9.81, and multiply it by your own mass, you've got the universal gravitation force equation. G times the mass of Earth times the mass of you over the radius of Earth squared should be the force of gravity that Earth exerts on you. And that should come to your mass times 9.81 when you're on Earth. You can actually use this to calculate the acceleration on any other planet. G times the mass of the planet over the radius of the planet squared. That'll give you what the gravitational acceleration would be there. You could use it for the moon, the sun, anywhere. Cool. So that's gravity. You've also got the normal force. Normal force is simply the force that a surface exerts on something else. Uh-oh. Hold on a sec. I heard a little computer bloop. So I want to make sure that we're still actually recording real quick. And yes, it says we're still live. Okay, good. Good. All right. So as I was saying, normal force is the force that a surface exerts on an object, and it's always going to be equal to well, no, it's not always going to be equal to something, but it's always going to point perpendicular to the surface. Always perpendicular. So if you're on a flat surface, it'll be straight up, but you're not always on a flat surface. Actually, the word normal literally means perpendicular. Normal force could also be called perpendicular force, and that's it. Sometimes it cancels out gravity, sometimes it doesn't. Another mistake I commonly see is people just plug in mg for the normal force. Normal force is not always mg. In fact, a lot of conditions have to be met before you can slap mg in for the normal force. One, you need to be on just a flat horizontal surface, and two, there need to be no other forces acting vertically. If both of those conditions are met, then yes. Oh, and three, you're not accelerating in the y direction. Whew. So if all three of those conditions have been met, then cool, normal force is mg, but only when all three of those are met. You got tension. This is just the force that a rope or cable exerts on something. It can only be a pull force. It can't be a push force. And rope, string, cable, whatever else. And it always just acts in the direction of the rope or string or cable. Okay, cool. That's tension. Friction, we're going to get into a little bit more in just a second here. That can be kinetic or static, but a couple of quick things about it. It's always parallel to whatever surface you're on. So if you're on a horizontal surface, it is horizontal. If you are sliding down a wall, then it's vertical, I guess. And if you're on a ramp, then it's just parallel to that surface. And it always resists motion. That can either be motion that is attempting to occur, or it can be motion that is occurring. Either way, friction resists it. And then you've just got all these miscellaneous applied forces. If I'm pushing something, I'm exerting a force on it. You got to include that in a free body diagram. Typical process for your force problems. One, you want to set up a coordinate frame. This includes deciding which direction your y-axis is pointing, which direction your x-axis is pointing, and which direction is positive and which direction is negative. It doesn't always have to be, the standard coordinate setup. In fact, sometimes it's easier if it's not. If I have a ramp and an object sitting on it, then it'll probably be easier to set up my coordinate frame where my y-axis is perpendicular to the ramp and my x-axis is parallel to the ramp. And you can decide for yourself which way is positive x and which way is positive y. It doesn't matter. As long as you stick with it through the whole problem, that'll be fine. But if I've got some force going up the ramp and I call it positive based on the way I've drawn these axes, that won't work out well for me. I'll need to put a negative in front of that, and vice versa. Cool. So once you've got your coordinate frame set up, you're going to want to break every force into x and y components. And a lot of times it helps to create a table here where you list the force, let's say the force of gravity, the normal force, friction, maybe some push force, I don't know, but some other force. And you'll want to list their x components and y components. Now, a lot of forces that I'm going to give you will only act in the x direction and only act in the y direction, or only act in the y direction. So, for example, on a standard problem, not on a ramp, the force of gravity would only have a downward mg and an x component of 0. When you break your forces into components, ask yourself if they're only in the x or only in the y, slap a 0 in the other one, and those are the easiest to break down. So if I'm pushing something to the right with F push, then I'll call my x direction F push. For that force, my y direction 0. Okay. It gets tricky when you start encountering diagonal forces. That's when you'll need to take an angle into account, treat the force itself as the hypotenuse, and then find its x component and its y component using sine and cosine based on where the angle falls. Cosine will go with the adjacent side, sine will go with the opposite side. Right? Once you've done that, and you got your table all set, add up all your x's to find a grand total x. Add up all your y's to find a grand total y, and do not forget your negatives as you do this, based on the coordinate frame that you set up. If you don't know them all numerically, just keep a variable there and leave it until you can actually come back to it. If you know the grand total x force or the grand total y force, set the sum of forces equal to this value. One thing you can always use, once again, is that the grand total x force is mass times acceleration in the x direction. The grand total y force is mass times acceleration in the y direction. So I could take this expression, set it equal to all my individual x forces or x components of force, all added together. And if you need to find the total force, sometimes you do, sometimes you don't, you can use the Pythagorean theorem where you've got your total x and your total y as the legs of the triangle. So your total force will just be the hypotenuse as a result. And it happens to equal mass times acceleration. All right. So I've already mentioned this 2 or 3 times. Don't forget this mess. Sum of all the forces in the x direction is mass times acceleration in the x direction. Sum of all the forces in the y direction is always mass times acceleration in the y direction. Done. Just a quick little heads up, since you're taking the time to look at this review. Take a look back at some of the ramp problems that we've done in the past. That's where I've aligned my y-axis to be perpendicular to the ramp, and my x-axis to be parallel to the ramp. And then I've rotated my coordinate frame so that I see it in a view that I'm used to, with y being straight up and x being to the right. And now my gravitational force has been rotated as well, a certain distance, a certain angle, whatever the angle of the ramp is, away from its original position. So be prepared to do that on the test. I have already mentioned this briefly, but make sure you understand the difference between weight and mass. Weight is a force. It's just the object's force of gravity acting on it, and that's it. It's equal to the force of gravity on the object. Mass is not a force. Mass has no direction, and it remains constant regardless of location. So your weight will change if you travel to a different planet. Your mass will not change if you travel to a different planet. Then we talked about friction. There's good old static friction. Static friction always pushes back with the same force that an object is experiencing that's trying to get the object to move. So if I'm on a horizontal surface and I push a big old refrigerator with a force of, let's say, 1 Newton. Oh, let me do forces in a different color so that it doesn't get lost in here. There we go. I push with a force of 1 Newton. Believe it or not, 1 Newton of force is a tiny, tiny little bit. And so I know it's hard to believe, but the fridge is not going to move. That's because the ground has pushed back with 1 Newton of force in the form of friction. If I push with 2 Newtons of force, that's still not very much. And the ground will push back with 2 Newtons of force as well. So the force of static friction can be 1, can be 2, can be 3, can be anything from 0 all the way up to some maximum value. That depends on the coefficient of friction, which is only a property between two surfaces when they rub together. It's a unitless property. That coefficient times the normal force is the maximum amount that static friction can handle. So the moment I push with that strength of force, this fridge begins to slip and kinetic friction takes over. Kinetic friction only has one value. So unlike static friction, it doesn't care how hard I'm pushing this thing. It only pushes back with one single value. And that's the coefficient of kinetic friction, which is a separate value, but also found from the two types of surfaces rubbing together. That coefficient times the normal force is the only value that kinetic friction will push back. So if I push the object harder than this, it'll speed up. If I push the object not quite as hard as this force, it'll slow down as I push it. And if I push it at exactly this force, I'll go at a constant speed. Cool. Typically, the coefficient of kinetic friction is less than the coefficient of static friction. It is harder to get something moving in the first place than to keep it moving. Hey, and that's what's on this slide right here, too. So as this kid is demonstrating, that wall is not easy to move, I guess. But once he gets it going, he can keep it going pretty easily. After we did a bit of friction stuff, we moved on to circular motion, and we got to the start of Module 4. A few terms that you need to know about circular motion. One is the amount of time it takes to go around the circle once. That's called the orbital period, or the period of revolution. It's denoted by a capital T because it's just a unit of time in seconds, but it's a special unit of time. It's how long it takes to go once. Frequency, meanwhile, is the amount of circles that have been completed in 1 second. So these are exact opposites of each other. Period is seconds per circle. Frequency is circles per second. So they're exact inverses of each other. Frequency is measured in hertz, and period equals 1 over frequency. We talked about angular velocity. This is different than your standard velocity in meters per second. Your angular velocity is the rate at which you travel around a circle. Specifically, it's how many radians of angle that you've traveled from your starting point in any given chunk of time. In order to calculate it, you can use this little equation right here. As you travel around a circle, there are 360 degrees. Converted to radians, that's 2 pi radians. So 2 pi radians for one trip around the circle. The amount of time it takes to get around that circle, that's the special T right there. That is the period of revolution. So if you divide that by the period in seconds, then you'll get the angular velocity in radians per second. And it doesn't matter where on this little radius you sit, your angular velocity will be the same if you're on, let's say, a turntable or a carousel or something like that. Linear velocity, on the other hand, is the type of velocity that you're probably a little bit more used to. This is the speed that you actually have. So how fast you're actually traveling, specifically in meters per second. Okay. Well, if you take a trip around the circle, you haven't traveled one radius, you haven't traveled one diameter, but you've traveled one full circumference of that circle. That's the path around the outside of the circle is the circumference. If you keep your speed constant, then velocity is just distance divided by time. The distance that you've traveled is one circumference. And the amount of time it took is that special unit of time. the time it takes to go around the circle once, the orbital period. So you can find the linear velocity as 2 pi r over t, circumference divided by period. Now these two equations are super similar, except this one has an extra factor of r. So if you ever need to get from linear velocity to angular and vice versa, you can always use this, where your linear velocity in meters per second equals your angular velocity in radians per second times the radius in meters. For a lot of these problems, don't forget your unit conversions. Be able to convert from kilometers to meters, be able to convert from years to seconds. Make sure you can always go back to your base units. Your base units, again, are meters, seconds, and kilograms, or some combination thereof of all of these. We talked about centripetal force. This is the kind of force that causes an object to go in a circle. Newton's first law, which we talked about at the very start of this thing, is that an object in motion will stay in the exact same motion, which means the same velocity, same direction, unless it's acted on by an outside force. So even if the speed is staying the same, you have to have a force to get something to turn. You have to have a force to get something to turn, even if the speed stays the same, because its motion has changed. This force is a centripetal force. Now, it's not a brand new flavor of force. It's not a brand new type. It's one of the types that you're already familiar with, one of those types from the usual suspects list. But those forces can act as the centripetal force, and you can set them equal to mv squared over r. One quick note, m is the mass of whatever is going in a circle. Okay. Mass of whatever is moving in a circle. By the way, since force equals mass times acceleration, the centripetal force equals mass times the centripetal acceleration, which means this. The centripetal acceleration is just the velocity squared divided by the radius. So if you happen to know the acceleration that's pulling something toward the center of the circle, you can find the speed that it has to have at a certain radius. Cool. I already mentioned that any force can act as the centripetal force. We played that little game, Name That Centripetal Force, right at the start. So ask yourself, which force is pointing toward the center of the circle? And which force is causing the object to move in a circle? Once you've decided on that, you can set it equal to mv squared over r. Sometimes it's gravity. Sometimes it's tension. Sometimes it's friction. Sometimes it's honestly literally any force you can think of. As long as it meets these criteria, that it's pointing toward the center and causing an object to move in the circle, then it's the centripetal force. We closed out talking about universal gravitation. This is an equation that works anywhere in the universe, where m1 and m2 are the masses of objects 1 and 2, and r is the distance between the centers of the two objects. That big G is just a constant. 6.67 times 10 to the negative 11th. It has units of Newton meters squared per kilogram squared, but you'll really only need to use the value there. By the way, this is one that I will provide for you on the test. probably right before the free response problems. That being said, I mean, it's not a bad idea to jot it down on your cheat sheet anyway, because then you've always got it to refer back to. Once again, on this test, I don't give an equation sheet. I leave that up to you. So like I mentioned at the very, very start, you're allowed one sheet of paper front and back to jot anything down. I don't expect you to memorize equations, but you really need to be in charge of deciding which equations you're going to bring with you to the test. That is about it. Cool. So I'm going to check with the large crowd of one here to see if there are any questions. But for the rest of you people, I'm going to go ahead and shut this thing down.